Chapter 16, Serverless, GraalVM, and Knative. This chapter covers producing native images with Spring Native and GraalVM, building serverless applications with Spring Cloud Function, deploying serverless applications with Knative and Kubernetes. In the previous chapter, you completed a long journey from development to production. You've built cloud-native applications using Spring and deployed them on a Kubernetes cluster in a public cloud. This final chapter aims to provide you with some additional tools to get even more out of your cloud-native applications. One significant benefit of cloud infrastructures is that you can increase or reduce resources on demand and pay only for what you use. Java applications have traditionally been very resource-intensive, resulting in higher CPU and memory consumption than other stacks like Go. Not anymore. Using GraalVM and Spring Native, you can compile your Spring Boot applications to native executables, which are more performant and efficient than their JVM counterparts. The first part of this chapter will guide you through taking advantage of this new technology. The second part of the chapter will expand on serverless architectures. Compared to CAS and PaaS infrastructures, serverless architectures move most operational tasks to the platform and let developers focus on the applications. Some applications are naturally event-driven and aren't always busy processing requests. Or they might have sudden peaks that require more computational resources. Serverless platforms provide fully managed auto-scaling features and can scale application instances to zero so that you don't have to pay anything if there's nothing to process. You'll learn more about the serverless model, and you'll build a serverless application using Spring Native and Spring Cloud Function. Finally, you'll see how to deploy applications using Knative, a Kubernetes-based serverless platform. Note: the source code for the examples in this chapter is available in the Chapter 16/16 Begin and Chapter 16/16 End folders containing the initial and final states of the project. See this link. Section 16.1, Native Images with Spring Native and GraalVM. One of the reasons why Java applications became widely popular was the common platform, the Java Runtime Environment, or JRE, allowing developers to write them once, run them everywhere, no matter the operating system. That comes from the way applications are compiled. Rather than compiling the application code directly into machine code, the code understood by operating systems, the Java compiler produces bytecode that a dedicated component, the Java Virtual Machine, or JVM, runs. During execution, the JRE interprets the bytecode into machine code dynamically, allowing the same application executable to run on any machine and OS where a JVM is available. This is called a just-in-time JIT compilation. Applications running on the JVM are subject to startup and footprint costs. The startup phase used to be quite long for traditional applications, for which it could even take several minutes. Standard cloud-native applications have a much faster startup phase, a few seconds rather than a few minutes. This is good enough for most scenarios, but it can become a serious issue for serverless workloads that are required to start almost instantaneously. Standard Java applications also have a higher footprint cost than other stacks like Go. Cloud services are usually based on a pay-per-use model, so reducing CPU and memory footprint means cutting down costs. This section will show you how to address this issue using GraalVM and Spring Native. Section 16.1.1, Understanding GraalVM and Native Images. So far, you've used the JVM and tools provided by OpenJDK, which comes in many distributions, such as Eclipse Adoptium, previously known as Adopt OpenJDK, Bellsoft Liberica JDK, and Microsoft OpenJDK. GraalVM is a newer distribution from Oracle based on OpenJDK and is designed to accelerate the execution of applications written in Java and other JVM languages. www.graalvm.org. By replacing a standard OpenJDK distribution with GraalVM as the runtime environment for your Java applications, you can increase their performance and efficiency thanks to a new optimized technology for performing JIT compilation, the GraalVM compiler. GraalVM also provides runtimes to execute code written in other languages like JavaScript, Python, and R. You can even write polyglot applications, including Python scripts in your Java code, for example. GraalVM offers two primary operational modes: The JVM runtime mode lets you run your Java applications like any other OpenJDK distribution while improving performance and efficiency thanks to the GraalVM compiler. What makes GraalVM so innovative and popular in the serverless context is the native image mode. Rather than compiling your Java code into bytecode and relying on a JVM to interpret it and convert it to machine code, GraalVM offers a new technology, the native image builder, that compiles Java applications directly into machine code, obtaining a native executable or native image that contains the whole machine code necessary for its execution. Java applications compiled as native images have faster startup times, optimized memory consumption, and instant peak performance compared to the JVM options. GraalVM builds them by changing the way applications are compiled. Instead of a JIT compiler optimizing and producing machine code at runtime, the native image mode is based on ahead-of-time (AOT) compilation. Starting from the main method, all classes and methods that are reachable during the application's execution are statically analyzed at build time and compiled into a standalone binary executable, including any dependencies and libraries. Such an executable doesn't run on a JVM, but directly on the machine, just like C or C++ applications. When using native images, much of the work that used to be performed at runtime by the JVM is now done at build time. As a result, building an application into a native executable takes longer and requires more computational resources than the JVM option. The GraalVM AOT compiler does not support some Java features out of the box. For example, reflection, dynamic proxies, serialization, and dynamic class loading require extra configuration to help the AOT compiler understand how to analyze them statically. How can we adapt existing Java applications to run as native images? How much configuration is required to support frameworks and libraries? How can we provide the necessary configuration for the AOT compiler? That's where Spring Native enters the scene. Section 16.1.2. Introducing GraalVM support for Spring Boot with Spring Native. Spring Native is a new project introduced to support compiling Spring Boot applications with GraalVM. The main goal of Spring Native is to make it possible to compile any Spring application into a native executable using GraalVM without any code changes. To achieve that goal, the project provides an AOT infrastructure, invoked from a dedicated Gradle Maven plugin, that contributes all the required configurations for GraalVM to AOT compile Spring classes. The project is one of the latest additions to the Spring portfolio, and it's currently in beta. At the time of writing, most Spring libraries are supported, as well as common libraries like Hibernate, Lombok, and gRPC. For Spring libraries not yet supported, or for your own code, Spring Native offers helpful tools for configuring the GraalVM compiler. For example, if you use reflection or dynamic proxies in your code, GraalVM will require a dedicated configuration to know how to AOT compile it. Spring Native offers convenient annotations like native hints and typed hint to instruct the GraalVM compiler directly from your Java code, taking advantage of the IDE auto-completion features and type checks. Note: Spring Native will come out of the beta phase and become part of the core Spring libraries, starting with Spring Framework 6 and Spring Boot 3, which are expected to be released in December 2022. In this section, we'll explore the features of Spring Native by building Quote Service, a web application that exposes an API to fetch quotes from books. Bootstrapping a new project with Spring Native and Spring Reactive Web. You can initialize the Quote Service project from Spring Initializer, start.spring.io, store the result in a new Quote Service Git repository, and push it to GitHub. The parameters for the initialization are shown in Figure 16.1.
Figure 16.1. The parameters for initializing the Quote Service project.
The project contains the following main dependencies. Spring Reactive Web provides the necessary libraries for building reactive web applications with Spring Webflux, and it includes Netty as the default embedded server. Spring Native supports compiling Spring applications to native executables using the GraalVM native image compiler. The resulting dependencies section of the build.gradle file is as follows.
See this code?
At this point you might ask, where is the Spring Native dependency? There isn't one. Where is Spring Native? The answer can be found in the plugin sections of the build.gradle file.
See this code.
When you add Spring Native to a project, you'll get the Spring AOT plugin, which provides the required configuration for GraalVM to compile the Spring classes, as well as convenient functionality for building native executables from Gradle or Maven. If you bootstrap a new project from Spring Initializer, you'll also get additional information in the help.md file about how to use Spring Native. Should you select any unsupported dependencies, you'll find a message warning you about it. For example, Spring Cloud Stream is not fully supported at the time of writing. If you initialize a project with Spring Native and Spring Cloud Stream, the help.md file will show you a message like the following. The following dependency is not known to work with Spring Native Cloud Stream. As a result, your application may not work as expected. Note: you can follow which Spring libraries are supported in the Spring Native official documentation. See this link. Next, let's implement the business logic for quote service. Implementing the business logic. Quote service will return random book quotes through a REST API. First, create a new com.polarbookshop.quoteservice.domain package and define a quote record to model the domain entity.
Listing 16.1. Defining a domain entity for representing book quotes.
Quotes are categorized by the genre of the book from which they are extracted. Add a genre enum to model this classification.
Listing 16.2. Defining an enumeration to represent book genres.
Finally, implement the business logic to retrieve book quotes in a new quote service class. Quotes will be defined and stored in a static in-memory list.
Listing 16.3. The business logic to query book quotes.
Note: since the focus of this example is the native image compilation with GraalVM and Spring Native, we'll keep it simple and skip the persistence layer. Feel free to expand it on your own. For example, you could add Spring Data R2 DBC and Spring Security, both supported by Spring Native. That's it for the business logic. Next, we'll expose the functionality through an HTTP API. Implementing the web controller. Create a new com.polarbookshop.quoteservice.web package and add a quote controller class to expose 3 endpoints for the following. Return all the quotes. Return a random quote. Return a random quote for a given genre.
Listing 16.4. Defining handlers for HTTP endpoints.
Then configure the embedded Netty server to listen to port 9101 and define the application name. Open the application.yml file and add the following configuration.
Listing 16.5. Configuring the Netty server port and the application name.
Finally, let's write some integration tests using the same techniques you learned in Chapter 8. Writing integration tests. When we bootstrapped the project from Spring Initializer, we got an auto-generated quote service application tests class. Let's update it with a few integration tests to check the REST API exposed by quote service.
Listing 16.6. Integration tests for quote service.
That's it for the implementation. Next, we'll execute the auto tests and run the application on the JVM. Running and testing on the JVM. So far, Quote Service is a standard Spring Boot application, no different from any other applications we built in the previous chapters. For example, we can run the auto tests with Gradle and ensure that it behaves correctly. Open a terminal window, navigate to the project's root folder, and execute the following command.
See this code.
We can also run it on the JVM or package it as a jar artifact. From the same terminal window, execute the following command to run the application.
See this code.
Feel free to verify that the application works correctly by calling the endpoints exposed by quote service.
See this code?
When you're done testing the application, stop the process with Ctrl-C. How can we compile it to a native executable and take advantage of instant startup time, instant peak performance, and reduced memory consumption? That's the topic of the next section. Section 16.1.3. Compiling Spring Boot applications as native images. There are 2 ways to compile your Spring Boot applications into native executables. The first option uses GraalVM explicitly and produces an OS-specific executable that runs directly on a machine. The second option relies on cloud-native build packs to containerize the native executable and run it on a container runtime like Docker. We'll use both. Compiling native executables with GraalVM. The first option requires the GraalVM runtime to be available on your machine. You can install it directly from the website, www.graalvm.org, or use a tool like SDK-man. You can find instructions on how to install SDK-man in Section A.1 of Appendix A. For the examples in this chapter, I'll be using the latest GraalVM 22.1 distribution available at the time of writing, based on OpenJDK 17. Using SDK-man, you can install GraalVM as follows.
See this code.
At the end of the installation procedure, SDK-man will ask whether you want to make that distribution the default one. I recommend you say no, since we're going to be explicit whenever we need to use GraalVM instead of the standard OpenJDK. Then open a terminal window, navigate to your quote service project, quote service, configure the shell to use GraalVM, and install the native image GraalVM component as follows.
See this code?
When you initialized the quote service project, the GraalVM GraalVM official plugin was included automatically. That's the one providing the functionality to compile applications using the GraalVM native image mode. Note: the following Gradle tasks require that GraalVM is the current Java runtime. When using SDK-man, you can do that by running SDK use Java 22.2. R17 Graal in the terminal window where you want to use GraalVM. Take into account that the compilation step for GraalVM apps is more prolonged, taking several minutes depending on the computational resources available on your machine. That is one of the drawbacks of working with native images. Also, since Spring Native is still in an experimental phase, you might get several debug logs and warnings, but that should be fine if the process completes successfully. From the same terminal window where you switch to GraalVM as the current Java runtime, run the following command to compile the application to a native image.
See this code?
A standalone binary is the result of the command. Since it's a native executable, it will be different on macOS, Linux, and Windows. You can run it on your machine natively, without the need for a JVM. In the case of Gradle, the native executable is generated in the build/native/native compile folder. Go ahead and run it.
See this code?
The first thing to notice is the startup time, usually less than 100 ms with Spring Native. It's an impressive improvement compared to the JVM option, which takes a few seconds. The best part of this is that we didn't have to write any code to make that happen. Let's send a request to ensure that the application is running correctly.
See this code?
When you're done testing the application, stop the process with Ctrl+C. You can also run the auto tests as native executables to make them even more reliable, since they will use the actual runtime environment used in production. However, the compilation step still takes longer than when running on the JVM.
See this code?
Finally, you can run a Spring Boot application as a native image directly from Gradle Maven.
See this code?
Remember to stop the application process with Ctrl+C before moving to the next section, which will show you another option for compiling your Spring Boot applications to native executables. It won't require having GraalVM installed on your computer, and it will produce a containerized native executable using cloud-native build packs. Containerizing native images with build packs. The second option for compiling Spring Boot applications to native executables relies on cloud-native build packs. Similar to how we package Spring Boot applications as container images in Chapter 6, we can use build packs to build a container image from the application native executable compiled by GraalVM. This approach benefits from not requiring GraalVM to be installed on your machine. Spring Initializer didn't just include the Spring AOT plugin when you bootstrapped the quote service project. It also provided additional configuration for the build packs integration available in Spring Boot. If you check the build.gradle file again, you can see that the boot build image task is configured to produce a containerized native image through the bp_native_image environment variable. While you're there, configure the image name and the container registry authentication as we did for the other Polar Bookshop applications.
Listing 16.7. Configuration for containerizing quote service.
Note: As you probably noticed when running the native image compilation process on your machine, it takes not only time but also more computational resources than usual. When using build packs, make sure you have at least 16 GB of RAM on your computer. If you use Docker Desktop, configure the Docker virtual machine with at least 8 GB of RAM. On Windows, it's recommended that you use Docker Desktop on WSL2 rather than Hyper-V. For more recommendations about the setup, refer to the Spring Native documentation. See this link. The command to use build packs and produce a containerized native image is the same that you'd use for JVM images. Open a terminal window, navigate to your service project, service, and run the following command.
See this code?
When it's done, try running the resulting container image.
See this code?
The startup time should again be less than 100 milliseconds. Go ahead and send a few requests to test whether the application is working correctly.
See this code?
When you're done testing the application, stop the container process with Ctrl-C.